Today's screencast is all about phase diagrams, specifically the calculations and lever rule associated with the phase diagrams. Here are some muddiest points collected from students, and in the screencast we will answer: what do alpha and beta represent? What is the eutectic reaction, and how do I find the chemical composition and phase fraction from a phase diagram? So if there is a particular topic that you wish to see, there are some hyperlinks right down here. If not, let's get on with the video. Here is a picture of a typical metal phase diagram. So something important to know is why we even have phase diagrams. Basically, a phase is a physically homogeneous part of a material system. When two metals are added together in an alloy, they usually are not completely soluble in one another, so they create separate phases, as seen by this diagram. This may be due to atomic radii difference or different crystal structure. Phase diagrams tell us which phases are present at a given temperature, which is on our y-axis, and a given nominal or overall composition. The phase diagram is a map that tells us at any temperature and nominal composition three things. First is what phases are present. Second, what the chemical composition of each phase or phases is. And three, what the phase weight fractions are. Most alloys have two or more phases because the properties are improved. So this is why we need phase diagrams. Now that we know why we need phase diagrams, let's define all the terms on this phase diagram. Let's start with our axes. Here we have temperature in degrees Celsius on the y-axis and composition or weight percent of tin in the overall structure on the x-axis. It is important to note that throughout this screencast and the next one, we will be using the example of lead and tin. Over here, we have 0% tin, and over here we have 100% tin. Now let's go into our single phase regions. Right here, this region, over here, this is called the alpha region. It is a single phase region which is lead rich, and it is solid. Over here, on this very small part of the graph, is the beta region. It is a single phase region which is tin rich, and it is solid. Up here, we have the liquid region. All of this up here is the liquid region. It is a single phase region made of liquid components, lead and tin. Now it is important to note that this line, so this V-shaped line going like this line is important because it is the liquidus line, meaning that anything above this line is a liquid. Also, this line right here is the solidus line, meaning that anything below this line is a solid. There are a few other important lines on this graph, one being this line over here, and the other being this line over here. Now this line on the left is the solubility limit of tin in alpha, meaning that if we started here and added even just a little bit more tin, we'd be in a two-phase region, and depending on the temperature, we would either be in the alpha plus liquid region if it was at a higher temperature, or at the alpha plus beta region if it was at a lower temperature. This line over here is the solubility limit of lead in beta, which means if we started here and added just a little tiny bit more of lead, we would be in a two-phase region and not a single beta region. So if we were at a higher temperature, we'd end up in the beta plus liquid region, and if we were at a lower temperature, we'd end up in the alpha plus beta region. Which brings us to our two-phase regions. This region right up here, so this region up here, is the alpha plus liquid region. It is a two-phase region with alpha and liquid, and it is a slush because there's solid alpha and liquid. This region over here is the beta plus liquid region, which is a two-phase region with beta and liquid, and this is also a slush for the same reason. Finally, here we have the alpha plus beta region. It is all of this region here, and what it is a two-phase region consisting of combinations of alpha and beta, and it is also a solid. We defined all of the terms on the previous slide except for the terms that had to do with the eutectic reaction. Now, by definition, the eutectic reaction is when liquid cools directly into the two-phase solid region of eutectic alpha plus beta. So when it cools, it doesn't go through either of these two regions first. So it cools directly into the alpha plus beta region right there. Whew, right down there. And in general, it looks like this. I just did it on our example phase diagram. The eutectic temperature is the temperature at which the eutectic reaction takes place. So in order to find it, we start here. At this point's very important. And then we head over to the y-axis, which gives us temperature. And so this value right here, which in our case is 183 degrees Celsius, is our eutectic temperature. The eutectic composition is the nominal composition of the eutectic reaction. So we find it, we start again at this point, and we go straight down to the x-axis, and we find it right there. And for us, it is 61.9%. The chemical composition of each phase at the eutectic composition is found by using the solubility limits, so these guys over here. The eutectic composition of alpha is the solubility limit of 10 in alpha at the eutectic temperature. So to find it, we start here. Then we go over to this point right here. And then we go down to the x-axis from there, and we read the value off. Now, it is given to us right up here at 18.3. So that means the alpha's composition at the eutectic temperature is 18.3%. 10. The eutectic composition of beta is the solubility limit of lead in beta at the eutectic temperature. So, again, to find it, we start here. We go to this point over here. Then we read down. Then we would read straight down to the x-axis. Right there. So, it's pretty high. But again, it is given to us right there. So that means beta's eutectic composition is 97.8% tin for our example. To review, we just reviewed the lead-tin eutectic reaction. It happens at this temperature, 183 degrees Celsius. We have the liquid phase cooling down into alpha plus beta region, so straight down. The percent composition of the liquid phase is equal to the eutectic composition, so in our case it's 61.9% tin, and then this goes into alpha plus beta. When alpha, remember we found it over here, it was 18.3% tin, and beta, which was over here, and it was 97.8% tin. And this is our specific, and in general, you have remember the liquid cooling into the two-phase solid region. So in the general case, you have the L being at the eutectic composition, cooling into the first solid, which would be the solubility limit of B, so whatever is on your x-axis in solid 1, so again, over here, and this, in general, the composition of solid 2 would be your solubility limit of A, so again, in this case, lead, in S2. So this is our general case, and this is our specific case. As a final note, any overall or nominal composition that is to the left of the eutectic composition is called hypoeutectic, and then any nominal composition to the right of the eutectic composition is called hypereutectic. So now that we've defined all of our terms, let's do an example phase calculation. We are asked for 40 weight percent tin and 60 weight percent lead, so this is our nominal composition at 150 degrees. Which phases are present, what is the chemical composition of each phase, and the phase weight fraction of each phase. So let's just find the place where we're talking about. So for 40 weight percent tin, so we go down to our x-axis and find 40% tin, right there. And then at 150 degrees, so go back to our axis, go up the y-axis until we find 150 degrees Celsius, and that's right there. And then when these two lines would intersect, so going up and going this way where they intersect, that would be the point where we're talking about. So for our first question, what phases are present, all we have to do is identify which region of the phase diagram we are in. And we are in the alpha plus beta region. So for the phases present, it would be alpha plus beta. Now we need to find the chemical composition of each phase. We know our overall composition is 40%, so 40% tin. Remember, we're talking about in terms of tin. Now we need to find our composition of alpha and composition of beta at our given temperature, 150 degrees. So, just like we did before with the eutectic temperature, we're going to find the composition of alpha by going over from our point, or from the y-axis, to this point right here, the solubility limit of tin in alpha at our given temperature will give us our composition of alpha in terms of tin. So over, or this way, and go down to our x-axis, and that will give us our composition of alpha, which for this given temperature is 11%. So this would be 11%, and this is talking about in terms of tin. Then for our composition of beta, it's again at 150 degrees, we go over to the solubility limit of lead in beta at our given temperature, which would be over here. Remember, these are solubility limit lines, and we go down from this point to the x-axis and read off the number. So in our case, it is 99% tin for our composition of beta. So now we've come to our most tricky calculation, the phase weight fractions of each phase. So what we do is we first start over here for our phase weight fraction of alpha. So we start over here, which would actually be, 0% alpha, right? Because this is our solubility limit, right? And then we head from there to our nominal composition here, which in this diagram is labeled as Q. So for our weight fraction of alpha, we do Q over the entire thing, which would be P plus Q, so this entire distance. And this is what we call the lever rule, or the inverse lever rule. And if we start from over here, from 0% alpha, going this way, we can remember that this distance is the one that we use for alpha, and not this one. So, mathematically speaking, Q would be, we would use this formula here, and we would read straight down to our composition of beta, which would be, again, 0.99, changing the percentages into decimals, and then minus our nominal composition, so minus 0.4, over, remember, P plus Q, so the entire distance, which would be 0.99, right? 0.99, again, minus the composition of alpha, so down, we found it, minus 0.11, and this equals 0.66. Now, for our weight fraction of beta, we start here, and we use this distance here, which would be P. So it would be P over the entire distance again, which is P plus Q, and mathematically P would be found using this formula. So our nominal composition, which again is 0.4, minus our composition of alpha, which would be 0.11, all over P plus Q, which would be composition beta, 0.99, minus composition alpha, 0.11, which would be 0.33. And just remember, for the weight fraction of alpha, you use this one, not this one, because that is the most common mistake. We've already gone over this calculation, but I'm going to show you a way in order to make your life easier and for this whole process to go a little bit faster. Using this table, we can organize our answers. So let's redo it really quickly. So phases present, we've given 40% and 150, so right there. All right, phases, we know we're in the alpha plus beta region, and then this now becomes our alpha column, and this now becomes our beta column. Chemical composition of alpha, start from our point, go over, down, left down, so that'd be 11%, tin. For our composition of beta, we go over, down. So that would be 99%, 10. Phase fraction. Now let's just approximate it first. We know that it would be this distance over the entire distance for the phase fraction of alpha. So this looks to be about equal to 2/3. This distance here, we can see that this is about equal to 1/3. So let's see how our formula stands up. Remember, this is our formula right here, and I've already gone through the mathematical calculations, but we've shown that our phase fraction of alpha would be 0.67 using this formula and our found values for the chemical composition of alpha and of beta and of our overall composition of tin. Once we have our phase fraction of alpha, we can use this formula right over here to find our phase fraction of beta. So plugging in all our numbers, we can see that our phase fraction of beta would be 0.33, and look at that, our approximations were really close. So this is how we can make our lives easier by organizing our values in a table. So let's see if we've answered all of our muddiest points. We've answered what beta and alpha represent. We've talked all about the eutectic reaction and all the terminology that goes with it. And we've talked about how to find the chemical composition and phase fraction from the phase diagram in multiple ways. So I've hoped you've enjoyed our discussion about phase diagrams. The next video is going to be about determining microstructures from the phase diagram, and so stay tuned for next time.